track that we have our hello. Good morning, all. I think you are able to hear me. So, welcome all to the Fovision series of webinars. Myself, Shyam, Technical Sales and Service Engineer, Fovision Instruments. About us, Fovision Instruments are in the field of scientific instruments for the past 20 plus years. So, next year we'll be celebrating our 25th year. And we represent Bruker NanoRacer division with their stylus profilers, optical profilers, and atomic force microscopes. And we are 20 plus people stationed in Delhi, Kolkata, Bangalore, Chennai, and we have our head office in Hyderabad. So we are constantly in touch with you people, sharing knowledge and educating you regarding the technicalities of the products we represent through webinars. So from the last year, we are conducting a lot of webinars, and in the series, this is a new one in this year, this new year actually. So wishing you a positive new year ahead actually. So today our topic will be on NanoRacer. NanoRacer is a high-speed AFM definitely, and to study the dynamic behavior of your sample, especially in the biological samples and the biological field, you need a high-speed AFM. So it will be the commercially available high-speed AFM from Bruker JPK. So we'll be explaining the technicalities and the capabilities of the tool to you. And today's presenter will be our application scientist, Dr. Cantilever Rao. He's our application scientist in head office Hyderabad. So he has pursued his PhD from Institute of Physics in the field of material science, and his expertise is in the field of microscopy, definitely. And he worked as a postdoc in RS University, and he has published like more than 30 articles in various scientific journals. And he will be the presenter today. Welcome, Dr. Raghav. And before I am handing over the stage to him, so I request you, all attendees, that the question and answer section is open, and it can be on the last of when we conclude the webinar. You can ask the last, and if you have any troubles or any queries in between, you can just drop a message in the chat box, and we'll be addressing everything. And if it is not possible, we'll be in touch with you through email. So thank you once again for joining. So we have some 10 plus attendees here. So we'll be starting the webinar now, and I welcome Dr. Raghav to take charge. Thank you.
Yeah. Thank you very much for the wonderful introduction, Mr. Shyam. It's my pleasure to deliver the lecture today. Good morning, one and all. And give me a second so that I will share my screen, and then we can discuss about the about this wonderful product of JPK with a very fast scanning rates and other stuff. Mr. Shyam, just confirm me that you can see my slides.
Yeah, Raghav. Yeah, it's fine.
Yeah.
It's fine. Everything is fine. Okay.
So, good morning, one and all, and welcome to the Fovision webinar series. And this is the first webinar in the new year 2021, and we are glad to introduce you our new and wonderful product of NanoRacer, a revolution in high resolution imaging due to its capabilities. And I will discuss about these capabilities first and foremost. Before going to the technical specifications of the NanoRacer, I would like to introduce our company to all of you, and then I will just cover a slide about the basics of AFM. And I don't know the complete background of all the attendees, so I thought it would be a helpful slide for understanding who are new to the AFM, or maybe just I want to refresh your memories about AFM basics, and then we will go to the technical details and specifications, and maybe we can look over a couple of examples why the NanoRacer plays a crucial role in understanding the molecular dynamics and its specialty in high-speed imaging. And then I will discuss a few points about its force measuring capabilities and also about the resolution. So before going to the technical details, I would like to introduce our company. And 4Vision Instruments is in the field of scientific instruments over 20 years. And we are the channel partners of Bruker NanoSurface division and also Bruker XRM division in India. And we have around 20 well qualified and trained people to assist the customers for various technical and service related issues and trainings and helping in the product designs and product implementation and understanding them and utilizing these products in their research. So with this, I would like to go for a brief introduction about me. I have pursued my PhD from Institute of Physics, Bhubaneswar in the field of material science, and my expertise, as Shyam mentioned, in microscopy. And then I have spent some 3 years of time at Aarhus University, Denmark, as a postdoctoral. So coming to the basics of AFM. So the AFM has basically three components. Like the first one we always look at is a cantilever, which is more crucial because this is the detection or this is the instrument which will detect the force of attraction or repulsion between the sample and the cantilever. And based on the forces, the cantilever will deflect, and this deflection has to be detected. So for that, we use a photo diode with a position sensitivity and a laser. So with a laser and photodiode is combination is a detector, cantilever is a sensor, and then we have a scanner unit. And the scanner unit will scan the sample. It can be either a sample scanning or a tip scanning based on the requirement of the users or based on the system configurations. So this is the basic system of AFM. So what it can give you? It can give you a topography in the nanometer scales, and it can give you a high resolution in terms of angstroms. So as you can see, the high resolution AFM image of graphite on the right side of the schematic, you can clearly see a high resolution hexagonal structure of the graphite of the carbon bonding. So this is about a spatial resolution. That means the resolution in terms of space. But in order to capture this image, we have to spend some time. So if the system is static, yes, we have enough time to do the measurement on top of the sample without having any modification. But suppose my system is dynamic, my atoms are moving, then within the within the given time or within the change of these dynamics, I need to capture my image. So that's called as temporal resolution. So the general AFMs in tapping mode, they can do a speed of 20 Hz. Then comes a different AFMs. So I will show you a family of JPK AFMs and their capabilities as a single slide to understand why NanoRacer is more important in order to get a good temporal resolution or time resolution. So this is a JPK family of Nano Wizard, where we have a starting system, our introductory system as Nano Wizard Sense Plus. And then you can move to Nano Wizard 4XP. The scanner and other stuff, electronics are different, and I don't want to discuss or don't want to go deep into the family, but this is the family with increasable capabilities. So Sense Plus, Nano Wizard 4XP, then comes the Ultra Speed, and then comes our new man, NanoRacer. So the speed of observations are also increasing, and I am not going to the numbers. If you are interested, maybe we can discuss at the end of this presentation if time permits. So coming back to the NanoRacer. So NanoRacer marks technology in terms of high speed imaging because it has a 50 frames per second imaging capability. So it can take 50 images in a second, and this is the fastest AFM available in the market, and it is especially designed to understand the dynamics of single molecules and DNA origami and protein binding and hybridization and dehybridization. All these dynamic features changes very quickly. So we need to capture these things. We have to have the capability of having these things grabbed within the time frame of their changes, and it is fully automatic system, so that the user no need to worry about the calibration or cantilever alignment. Maybe if some of you know about the AFM, then you are always try to adjust your feedback or gain to be high, and you need to focus your cantilever and all these things. If you are spending time on these things, then you might lose your dynamics. So this system comes with automatic setup, so that everything will be automized. So with this automation, you will obtain outstanding performance from the system. So I would like to go more deep into these specifications, like it it designed such that your sample dynamics can be captured a very fast and easy way, and then it gives you a situation that you can do in the real physiological conditions. You want to put your proteins under physiological conditions to observe and understand their real time behavior. So you will get that, and with that you will get a outstanding resolutions. So you are no need to compromise about outstanding resolution, and this outstanding resolution will be possible if we have a high stability and accuracy. Then only we can get high resolution and reproducible results. As I earlier mentioned, this gives you an automated setup, and the time taken for this automatic setup is less than a minute. And the sample loading and probe loading is very easy. And you don't need to do a calibration thanks to the closed loop scanner. This system comes with all three directions closed loop scanners. So these closed loop scanners will avoid the calibration procedures, and the new software graphical user interface is renovated so that you will get the scientific output much easier and much faster. The data analysis is redefined such that you will get more information from the samples, and we have advanced and intelligent imaging control algorithms such that you will get a sharp images. Then the capabilities of the product. So it's newly developed high-speed head and scanner. It has a newly developed high-speed head and scanner to perform these images at such faster rates without having much impact from the noise or other stuff. And it is optimized especially for small and medium cantilevers. And we have employed cutting edge electronics to capture the uh, outcome of the sample without having any delays or with lesser delays. And we have developed this system as a robust system such that it has good stability and less thermal drift, and all these things will come into the picture. And we have used high bandwidth digital electronics such that the response times will be minimal and the data processing speeds will be much faster compared to our previous versions. And as I mentioned, this system works with a closed loop scanning in all directions like X, Y, and Z. And we have provided a high voltage amplifier such that it can drive the piezo's with low noise and get a perfect scanner drive for the scanning of the AFM. So this is the uh, NanoRacer picture. So here you can see the first image. So I hope you can see my laser pointer. The first image on the left of yours is the NanoRacer picture, and then here the head is flipped up so that you can see the inner parts. And the third picture, you can take out the scanner completely out and you can prepare the sample outside of the lab. Maybe you can prepare in somewhere in the lab and bring back the scanner and put it inside. Just plug it and do the experiment. So this provides you that feasibility so that you can carry your scanner out and prepare the sample outside and bring back to your AFM to do the measurements, such that you will get good results under physiological conditions. So the key specifications of this system is the scan speeds are up to 50 frames per second with a scan range of 100 by 100 nanometers square. So it is a small area, but it's more than enough to do such single molecule dynamics, and it can give you a 10K pixel image resolution with a good resolution. And the cantilever can be driven by photothermal tuning such that we can do a clean drive option. And we have one more IR source other than the cantilever such that you can use that IR source to excite your samples. And we have a highest bandwidth of the detector as 8 megahertz for high speed signal capture. And coming to the scanner unit, it has a 2 cross 2 cross 1.5 micrometer scan range for normal operations, and for faster operations, it can work in a 100 by 100 nanometer square. And a 90 picometer sensor range in XY sensor noise, and in Z direction, it has 40 picometer noise levels. And the highest resonance frequency of Z axis is more than 180 kilohertz. And it can take a sample size of up to 3 mm diameter. And we have a high resolution camera, motorized camera for auto focusing and auto tuning, auto detection, and everything can be done with high resolution camera. And we have a 2 probe holders available with this system. One is standard with a direct drive, and another one is called 3-port smallest volume cell. And this 3-port smallest volume cell works with photothermal tuning only, and this has a special capability to take a microliter volume with Hamilton injection. So with the Hamilton injection, you can inject a microliter volumes of the your samples into the system, and you can observe. Coming to the scanner controller, it has a new Vertex 2 speed controller. It is designed with optimized parameters such that it will give you a high throughput and high performance with faster acquisition rates. And its position sensors, readout technology are highly sophisticated so that the noise levels will be minimal. And we have an additional signal access module so that you can access the signals to the external use, and you can do your own programming and user defined programming to perform the experiments in your own way. And it has an additional HV amplifier, and that amplifier is used for driving the piezo for a low noise and perfect scan drive. And this system is equipped with peak force tapping mode, one of the trademark of Bruker for doing the challenging samples. So we have a new workflow for GUI. The graphical user interface is so interactive with the customer that it will allow and assist the operator or the person who is operating the system, and it will help to perform the experiment with much faster and quicker ways to get your data, and it will give you a step-by-step guide so that how you will set up the experiment, how you are carrying out the experiment, how you are taking out the measurements, and this will enhance the research output. And there are a wide variety of modes are available, like standard modes like high speed imaging, tapping mode, contact mode, tapping mode with phase imaging, contact mode with lateral force microscopy. And besides that, there are force measurements are also available, and the force measurements are static and dynamic spectroscopy. And also you can do advanced force mapping. And there are few optional modes are also available, like peak force tapping, advanced AC modes, higher harmonics imaging and nanolithography and nanomanipulation. And you can design for force measurements, you can design, and JPK ramp designer will help you to design your force measurement. And we have an experimental control feature to remotely control your experiments. So with this, I am moving to the examples. So this is one of the DNA hybridization, dehybridization dynamics, where a metastable bubble will form and closes. So as you can see in the video, the bubble is forming and changing its shape, and it will close down after a few moments. So once we capture the data, we need to analyze this data. So in order to analyze this data, what I can do is we can take out the frames at our interesting time zone, and you can take out and you can look at how the sample or how my DNA hybridization or dehybridization is taking place. So as you can see, the shape change of this metastable bubble can be taken out as frames at different time intervals. And this experiment was performed with a frame rate of 37 frames per second. That's pretty fast. So here you can clearly observe the shape change of a bubble in the uh, below slides, below photographs, and you can determine the shape of that metastable bubble and closing of the metastable bubble with respect to the time frames. Coming back to the second example. So in the case of streptavian bindings, these streptavins will bind and they won't stay for longer. They have some time. Within that time, they will bind and again they detach, attach and detach. And this attach and detach mechanism will take place within a certain time scale. If the conventional AFM, if we use a conventional AFM to look these attachment and detachments of streptavin, then either we will end up an empty site or completely occupied site, not the complete dynamics. So in order to understand these complete dynamics, if you employ the NanoRacer, as you can see here in the video, see here one of the streptavin was disappeared, again second, now again it is reappearing. So these dynamics can be understood properly such that we can take out the statistics of these attachment and detachments of the streptavin, and we can do the analysis of these attachment and detachments with respect to the time. How many streptavin bindings happen at a particular site, and in terms of time scale, like 10 seconds, 20 seconds, 30 seconds, or milliseconds or microseconds. Based on their dynamics, our time scale can be set, and based on that, we can calculate at each site what is the occupation or removal or detaching of the streptavin. And then comes to the annexin protein. So this annexin protein is crucial in the cell repair. So in order to understand the dynamics of this annexin, we have performed an experiment to understand the reconstruction of this annexin. So here in the video, you can see the shape changing dynamics of this small area, and this was taken at 3.4 seconds per frame. So 3.4 seconds was the time to capture one frame, and it was obtained in a range of 145 nanometer by 120 nanometer in the x and y axis. So this is how we can understand what's happening and how the crystal structure or how the structure of this annexin is changing during the dynamics. Sorry. So here what we are observing is the defect dynamics. One second. So here what we can see is the crystal growth. So here you can observe there are two different particles are present. So after some time, the smaller particle will coagulate with the bigger particle to grow much bigger. So this growth or dissolution of the smaller particle. As you can see, the dimension of the smaller particle is slowly decreasing and it's mixing with the bigger particle. So the dissolution or growth of these annexin on a lipid membrane can be observed, and try to understand how it will help in annealing process or healing process of the cells or during the cell repair, how this behaves. So as you can see clearly, the dimension of the smaller particle or the size of the smaller particle gradually decreases and it will disappear. And we can also look at the edge dynamics, how the edge dynamics or how the edge structure is changing with respect to the time. Earlier we have seen the reconstruction of the entire particle, but we can see only the at the edge how the reconstruction is changing or how the edge atoms are molecules are rearranging themselves. So all these things can be observed. So besides having a high speed, it doesn't compromise on its resolution, as earlier I mentioned. So here you can see a lattice resolution image of mica inside the fluid. So you can see the left one is the mica image inside a fluid, and the FFT shows its crystalline structure and it's the mica structure, how the mica structure is there. So with NanoRacer, you can get high speed imaging, and also you are not compromising on your resolution. So you are getting a good resolution, good speed to perform the experiment. And as you can see here, even we can scan much smaller areas like 6.5 nanometers with 1.65 seconds per frame. And this is also done under fluid. So it gives you uncompromised images at high resolutions with high speed imaging capability. So besides imaging, as I mentioned, the force measurements also can be done on the samples. So even though it is moving at a faster rates, it can clearly detect between the sample and the substrate. So as you can see, we can draw out the force curves for DNA origami as well as the mica, and we can clearly distinguish between both the force curves with precise resolution. So having high speed, high resolution, and now we are having good detection of the force and good detecting capabilities of distinguishing between the sample and as well as the substrate, so that it will give us the information whether we are on the sample or on the substrate also. So this will help to do the experiment precisely on top of the samples only. So here we are doing a fast force spectroscopy on a GB1 protein with high pulling rates like 20 micrometers per second velocity, and we are acquiring the data with a 1 megahertz speed. That's pretty fast, and we are getting repeatable, reproducible results such that we are getting a good information with much faster times are much quicker, such that we can perform these experiments on multiple samples. So with this, I would like to conclude the presentation, and I'm welcoming you for your questions.
Thank you, Dr. Raghav. It was a very interactive and very wonderful presentation. And for the attendees, actually, the question answer section is open. So you can raise your hand, and we can unmute you, or if it is even also you can type in the chat box so that it can be addressed by our Dr. Raghav.
Hi Raghav.
Yeah.
Yeah, there is a question from one attendee.
Yes, please.
Okay, it is from Mr. Akshay Gaikwad. He's
Okay.
asking how many times a single AFM tip can be used.
This actually depends on the condition of your sample and the way you are measuring. If you are measuring in contact mode, it's different. In tapping mode, it's different. If your sample is soft, then it depends. And if the sample is hard, it also depends. So we cannot clearly say a certain number of times, but if you are properly using, you can use a tip. Depends on your measurements also, like maybe four to five times to 10 times. And it also depends on your scan area. If you are scanning larger areas like 2 micron by 2 micron or 10 micron by 10 micron, then also you need to change your tips frequently because you are using the scanning for longer times and with larger forces. So that also depends. So there is no hard and fast rule that the tip will work for this many times. Until unless you are getting a good image, your tip is good to go.
Okay, thank you very much, Raghav. And another question from another audience is what is the radius of the cantilever tip?
Oh, this is a good question, but actually, the radius of the cantilever tip varies for different tips. Like if you are working with tapping mode, the radius is typically 1 to 2 nanometers. If you are working with a KPFM, then the radius is around 10 nanometer. If you are working with the CAFM, again, it's a metal tip and it has a pretty sharp, like 5 to 6 nanometers. So it depends on what you are working and which mode you want. And if you want to work with force measurements, definitely your tip should be a little blunter compared to the tapping mode or high resolution imaging. So again, the size varies from like 1 to 2 nanometer to 10 to 15 nanometers based on our application and tip.
Okay, Raghav, thank you very much. And we will wait. Yeah. Okay, we have another question from Mr. Akash Gaikwad. Is there need to sample preparation? Is there any sample preparation?
This is also a very specific question as per as my knowledge, because if you are working in biological samples, yes, definitely you need a sample preparation. If you are working with semiconductors, I say no. But if you are working with nanomaterials, especially 2D materials, again, yes. And it also depends on, again, based on your measurements. Normal AFM for semiconductors, there is no sample preparation. But you want to look at EFM or CAFM, conductive AFM, you want to get a tuna measurements or current measurements, then you need to prepare the sample and you need to apply the bias. So you have to stick the sample with the stage using a silver paste and you make conducting path so that whatever the applied bias applied to the stage has to transform up to the top of the sample and you will get a uniform conducting path to get the measurements. So it's like a vast thing to discuss, but depends again, same, depends on the sample condition. If you are working with nanoparticles and you want to do a force measurement, then you need to fix these nanoparticles to the substrate such that if I am moving my tip and applying the force, the particle shouldn't move. If the particle moves, then we will get a wrong result.
Okay,
So
Raghav.
I hope that will give the answer to him.
Yeah. Raghav, we will wait some more minutes if anybody. Yeah, there is a question from Mr. Dr. Shiva Prasad. Conventional AFM can adjust feedback gain in scan analysis mode, but what is the uniqueness in NanoRacer except high-speed imaging?
Scan assist is a software mode where you have to select the area, like what is your region of interest. Then it starts automatically adjust feedback and gain. But before that, you need to adjust the cantilever and laser focusing and maintain your zero at the zero. In case of the scan assist also, you need to do these primary things and you need to engage. There is no auto engage. You need to engage through the software. But in NanoRacer, you no need to do anything. You just put your sample and switch on, go to the measurements directly. Everything will be taken care by your high-speed camera. That's what I said. Auto adjustment, auto tuning, auto alignment, auto capture, and auto detection. So if you are doing scan assist, the scan assist can do auto tuning, auto adjustment of the feedback, gain, scan parameters. But before that, you need to choose ROI, region of interest. Whereas in NanoRacer, nothing. You can directly go.
Yeah, Raghav, another question from Akash Gaikwad. Any important precautions during AFM operation?
Yes, there are a lot.
Please explain the.
Maybe I will give you a couple because there are a lot of things to take care during AFM operation. But all these things, I don't think this is the right platform to discuss about all those things. But I will give you a couple of precautions. Like during the engage, you have to be careful such that your tip shouldn't hard landing on top of the sample. So if the tip hard lands on your sample, then you have a problem and you need to follow the user guide for sample height. Like if the sample height is 5 mm, your sample should be below 4 mm only, not 5 mm. There should be always like 1 mm below the recommended, such that there won't be any accidents happen during the measurements. And make sure you never touch the tip either with this either with your tweezers or hand gloves, whatever it is, because of the small diameter. If you touch the tip might broke, tip might bend. The bending can cause artifacts in your sample. So there are a lot more precautions, but these are to name a few.
Okay. Raghav, another question from Dr. Pratin Datta.
Yes.
Okay, this is indeed a very informative presentation. What is the reason to use blunt tip when force spectroscopy measurement is taken?
This is a pretty simple answer. Like you have the pressure is like force by area, and if you want to use a very sharp tip, so if you are going to uh, apply force on top of the sample, you have a very small area to interact. So that will create a lot more pressure on top of your sample. So sometimes your sample might damage, or sometimes your tip might damage. So we use a little blunter. No, it's not too much blunt. Like maybe the normal high resolution tips have 1 to 10, 2 nanometer diameter. These tips are like 10 to 15 nanometer diameter.
Okay. Yeah, Raghav, we have another question. In this automation, how we detect sample for selecting region of interest?
Sir, generally the scan area is within 100 nanometer by 100 nanometer for your high-speed AFM imaging. So your sample should be within this region. So most of the times your camera will detect the samples, and we are using a small amounts. So most of the times the camera will take care of all these things, and it might it will scan the area to detect the sample where the sample present. As I said, it can distinguish between the substrate and the sample also. So I hope this answer his question, or
Yeah.
still he wants more technical details.
Okay, thank you very much.
Yeah, thank you.
Yeah. Shyam, over to you.
Yeah. Thank you, Dr. Rako, for the clarification. So I think if you don't have any further inquiries, you can close the presentation. And if you have any further doubts, you will be receiving an email for the feedback. Please submit the feedback also. You have our email IDs, and you can ask any question, and we are approachable anytime. You can just drop an email. We'll get back to you with the answers. Or sorry, we have another question from Dr. Shiv Prasad, I think. Uh, he was asking, in this like automation, whatever you have mentioned.
No. The question is, I don't think camera can differentiate substrate and DNA. Sir, as I said, I am not saying camera. So it's like integrated system of camera, probe, and detection. So it's like a single unit. That's what. It's a high resolution integrated camera cantilever detection system, sir. So it's not a simple camera. So it's an integration system with the scanner. So the scanner will take care and distinguish between the substrate and your sample. That's what I meant. Maybe I wasn't able to communicate or convey my explanation proper way. So here the camera is not like a simple camera. It's an integrated camera which is linked with cantilever, photo detection system, and camera as a combined system. That's what I mean camera. I hope this will give a brief idea about what I meant.
Yeah, Raghav, we have another question from Gurpender Singh. What are
Yes.
the demerits of using NanoRacer?
Everything has its own merits and demerits. If you want to have a large scanning areas, then NanoRacer cannot be used, and it always uses a smaller cantilevers. So if you want a high forces like maybe bigger forces like nanonewtons or more than that, then there might be some limitations. Maybe they will come up with a new idea to take care because it's just launched product. So we also don't understand completely about the demerits of the system. So I think these could be couple of demerits, but we are not sure what are the demerits coming up. Till now, a lot of people have used for a specific applications. It's not like generalized AFM, so that might be a demerit. It's especially designed only for the molecular dynamics and high resolution, high speed experiments. Maybe if you are a bio people, I can give us one problem, not a demerit, but one problem that you cannot integrate NanoRacer with your IOM. Maybe that could be one thing. Yeah, that's from my side. If you still have anything, please let me know. Hello.
Yeah, Raghav, nothing. Okay, as of now. Yeah. Raghav, another question from Dr. Rakesh Zar. Can we use powder samples? Any problem getting sticking with tip?
As I earlier mentioned, when you are using a powder sample, you need to prepare the sample properly. If you haven't prepared the sample properly, or your adhesion properties of the substrate and the powder is weaker compared to your tip, then you lost your tip because it will contaminated by your particles and you have to use another tip. That's what it's also like a precaution. You need to understand adhesion behavior between your substrate and your nanoparticles or powder sample. So if the powder sample was not properly stick to the substrate, then it will, during the scanning, it will pardon me, it will get attached with the tip and the tip will be contaminated and you will start seeing the artifacts immediately. So yes, it can have problems. Moisture on the samples. Okay, I got one more question. Any effect of moisture in sample? In principle, no, because we are using silicon nitride, which is a stubborn candidate. It won't have any effects from outer atmosphere like oxidation, moisture, humidity, all these things. But in some cases, it might. But most of the times, no. I say no effect of moisture. Yeah, thank you.
Yeah, thank you, Dr. Raghav. So as of now, no further questions.
Yeah, thank you, Shyam. And it would be a great pleasure to interact with all these audience. And thank you, one and all, for taking time and attending our webinar. Yeah, Shyam, you can take over, please.
Yeah, thank you, Dr. Raghav. Said we'll be sending an email for your feedback. Please reply. And if any further doubts are there, you are free to approach us anytime. We are there to support you technically. And for further inquiries, you can contact us directly. So thank you. So we'll be sharing further information regarding our webinar. So please try to attend the one which your application covers your application. And thank you all once again, and thank you, Dr. Raghav, and thank you, Sadhi sir. So so we'll be closing this webinar. Thank you all.